Alright, in this video we're going to sort of do out the transfer function for this circuit, and it's sort of actually, it's a C, and it's a nested RC. So from doing filters so far, we should probably know that actually something like RC like this, going from, you know, input to output right here, this will actually be a low pass filter. So this is actually going to be very similar to that. It's going to be two nested low pass filters. Solving out the transfer function doesn't become just a simple matter of multiplying this one by this one, because you end up having loading. So like if we just had, for example, the left half of the circuit right here, so let's just circle it right here, it'd actually be, if this part right over here wasn't in existence, it would be pretty easy to solve. We've done probably this one before. This was done in lecture. This was most likely done in recitation a few times, right, and in homeworks a ton. It gets more complicated, however, because there's now a second RC here, and it's sort of loading this one, right? So whatever formula we came up before, we can't just multiply it by 2, because that formula, when we derived it, would have been assuming there was nothing here. There was no other impedance. This is the same thing that we actually saw in one of the early labs with the DACs, or any sort of nested voltage dividers, right? So like the problem is the formulas you use in figuring out this voltage, right, given some input, right, this gets changed once you add in a second voltage divider, right, if you wanted to measure this. So what we need to do is sort of solve this one. It's the same exact math, it just becomes complex. As a little bit of an aside too, this sort of circuit where you have a RC, 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 this is actually a model of a cable, or any sort of transmission line of information, a simple model anyways. And what's neat, what we'll see out of this is actually this sort of indicates why, if you ever go and read up on USB specs or any sort of data transmission specification, there'll be certain data transmission limits, right? Because you're usually transmitting ones and zeros, sort of like this, you know, over time. And what happens is transmission lines like this end up rounding out these signals. They low pass them. The sharpness of a square wave is a result of high frequency components whenever you break it down into its FFT. And because this sort of filter will actually pass lower frequency components with a higher preference than higher frequency components, it will actually end up removing a lot of this, and you'll end up with signals that sort of look, you know, like this, and you'll get a weird phase lag, and eventually this can degrade to the point when you have a long enough cable where, you know, it's like this, and then you have a hard time discerning what is a 1 and what is a 0. Anyways, let's come up with a expression for the output voltage V out as a function of j omega over V in as a function of j omega. And I'm going to solve it first just for the original transfer function, and then we can, depending on timing, go and look at the magnitude and the phase. And we'll call this the transfer function h j omega, like this. And it'll have some sort of magnitude and phase component with it. So when I'm solving a circuit like this, the problem is you could come up with some big nested, so R and C are in series, and then they're in parallel with Z, and then those things form a voltage divider together. I guess, and you can go about doing that. I guess my strategy with this is, let's go in and, if I analyze first this side, right, this is a voltage divider, right, in the complex domain, right? It's going to be 1 over j omega C over R plus 1 over j omega C, right? That'll be the output voltage here as a function of whatever this input voltage is. But we don't know that input voltage, and what further makes it complicated is this voltage here that we would calculate is actually going to be a function of all of these together, and then this. So what I'm going to do is actually going to label some unknown phasor voltage right here, VA, and I'm going to just say that V out will be based on whatever VA is, and then just do the voltage divider that we would come up with for this, the impedance divider. I'm sort of kicking down the road calculating VA for a moment. We'll figure that out later, but I want to come up with an expression for V out first. Oh geez, what did I do? And then we'll, as a function of VA, and then we'll figure out what VA is in a little bit and multiply them together, and then life will be okay. So that would just be pretty simple. It's going to be bottom impedance over total impedance right here as a function of VA. So it would be 1 over j omega C over 1 over j omega c plus r, right? The impedance of a capacitor is 1 over j omega c. The impedance of a resistor is r. I don't like this fraction. It's kind of gross looking, so I'm going to multiply top and bottom by j omega c. So that's saying VA, this is going to be, this cancels, so it'll be 1 over 1 plus j omega c r. Good. Now let's figure out what VA is, right? That phasor. So let me copy this whole thing for a moment. And just so I don't get lost in my math, I'm going to box this answer in from up here just for later use. All right, so we want to figure out what VA is. And really that's going to come down from the another voltage divider situation, except it's going to be this combination, and it's going to be a series then parallel combo, over R plus that same thing right here. So in a very general form, it's going to say VA will equal Vin times Z complicated, let's do Z sub C, over Z sub C plus R, right? And we got to figure out what Z sub C is. So Z sub C will equal this in series in parallel with that. So what would be the nicest way to do it? Let's just do it out the there are two things in parallel. Let's see what comes out of the other end. I haven't done this thing through yet, so who knows? So it'll be R plus 1 over j omega c times 1 over j omega c over R plus 1 over j omega c plus 1 over j omega c. So that's this combo in series in parallel with this single value on its own. So this actually won't be too bad, right? Let's multiply, well, let's make the whole thing over 1 over j omega c, might as well. So that would mean this becomes what? R j omega c plus 1 plus, oh wait, times 1. Okay, and then it'll be, yeah, I guess we could just do R j omega c plus 1 over j omega c. Okay, I'm liking this so far. So this and this will cancel out. So we're going to be left with, I'm going to move here. This will be what? So this will end up being what? So negative, so this comes down to the bottom, right? Another way to write this would just be j omega c times this thingy. Foil this, or whatever you call it, so it'll end up being negative r, because you have your j times j is negative 1, the omega, so omega squared, c, these combine together, so it's just going to be plus 2j omega c, like that. Okay, that doesn't look too bad. Okay, so this is fine. So then we got to go back up here, and remember that VA is actually a function of Vn times this whole mess right here, which it is kind of a mess. So it'll end up saying what? VA equals whatever Vn is in the in the complex domain, this thingy. So it'll be, oh boy, R j omega c plus 1 over negative r omega squared c plus 2j omega c over that plus r. Gosh, why did I pick this? J omega c plus 1 over negative r squared. Whoops, not that. Plus r. Okay, that's fine. That's kind of gross. Let's multiply the top and bottom by the denominator here to get rid of it, or at least clean it up a little bit. So this will actually end up equaling Vn phasor r j omega c plus 1 over r j omega c. I feel like that's not right. Oh no, that's right. Plus 1 minus r squared omega squared c plus 2j omega r c. Great. All right, this isn't bad. So really what this is saying is what? VA equals V in times that stuff. And then up here we got what? V out equals VA times this stuff. So let's do this out then. This will be what? V out equals this mess times this thing right here. Interesting. And then the transfer function itself would just be V out over V in. And these are all as functions of j omega, right? So this is sort of going to equal h of j omega. And then let's copy this thingy down here again. Okay, and let's look at this messed up thing. Ooh, actually, wow. Look at that. These cancel. How about that? Oh, this isn't too bad now, right? H of j omega is going to equal 1 over... Oh, this is looking pretty good. This is actually what? 1 minus r squared omega squared c. These are the... Yeah, okay. Plus 3j omega r c. Interesting. Was not expecting this to come out at the end. Okay, so I got this as a transfer function out of this. So anytime I get to the end of a transfer function like this, and I'm kind of, I don't know, I'm not sure if it's right or anything, what I would maybe do is go back and maybe let's do some sort of sanity checks on it. So what I'm going to do is let's copy this down to the bottom here. And I don't know, I just want to compare it a little bit. Right, so at... let's do it this way. Oops. What I'm going to do is just sketch out or note down some things that I sort of observe at different frequencies, just to make sure this thing actually kind of makes sense to me. So for example, when omega equals 0, so basically at DC, what is the equation telling me that my input to output relationship is going to be, and what is the circuit as I know it from like analyzing capacitors and resistors going to tell me? So with the circuit, just to start with that real quick, right, we know at DC capacitors act as opens, right? So V out should just be V in, right? Because this is going to look just like, if I draw it out real quickly, a resistor, an open, a resistor, an open, and then, right? And sure, there's the wire down here. But basically, this is just a wire going to here. And yeah, and whenever we're analyzing V out, this is an open circuit, right? So there's no current flowing through, so whatever the voltage is here will be the voltage here. So the circuit tells me the magnitude should be 1, right, of the gain. Don't worry about phase, I guess. That is actually what the equation's telling me too, right? If I plug in omega of 0 and 0, I get 1 over 1. Oh, so that's good. All right, so that makes me feel a little bit better. Another thing would be to do is what's going to happen at very, very high frequencies. So let's say at omega going to infinity, so high AC. So what we know at, this was also just for notes, then at omega equals infinity, or goes to infinity, whatever, we know capacitors act as shorts at high frequencies, right? So this ends up looking more like resistor to short, resistor to short. So there's going to be 0 out. So the circuit's telling me mag will be 0. Okay? What is the phase going to look like here? I mean, what's the transfer function going to tell us? Well, it's going to say a couple things. One is at very high values of omega, if we think back to Calculus 1 or maybe pre-calc, wherever you learned about limits, if we look down on the bottom here, there's an omega squared term as we're looking at limits with omega. That's going to dominate, and that's a negative omega squared term. So that's telling us for very high omegas, this is going to go negative in the denominator. So that's, and then basically then a gigantic number in the denominator, so it's going to go to 0. And the phase, importantly, you'll have a 1 over a very large negative. That's going to be plus or minus pi, depending on how you want to approach that. I would say that is, it doesn't matter, right? They're the same thing. But okay, so these actually, just from a analysis perspective, these kind of line up, these kind of line up. So I actually feel okay about this expression. That's kind of cool. If we were to go and just sketch this out, and I'm not going to be too quantitative with it, just qualitative, and I'm going to just build on the analysis we just did actually right here. What will the frequency response of this equation look like? So if we do the mag right here, and remember these are logarithmic scales. Right, we know at DC we're going to have a gain of 1, or 0 dB, whatever. We'll just make a 1 right here. Don't worry about the dBs. And then at high frequencies, they're going to be down at 0. And there's going to be some sort of set of poles right here, and it's going to roll off, hit them, and go down like this. I'm not too obsessed right now about what those poles are. The phase, on the other hand, is going to start at 0, and it's going to drop to minus 180. Whoops, let me line it up. You'll basically be about halfway down in phase when this thing's at its 3 dB or 6 dB spot. Sorry, this is a very poorly drawn graph. But this is just a rough sketch out of the magnitude phase of this transfer function. But in general, what I want to obsess over a little bit is actually this thing right here. So the magnitude, right, we can see for higher and higher frequencies, the transfer function drops, right, as a function of omega. And that's kind of cool because that's telling us that this series of RCs nested kills, it's a low-pass filter, right, and it's actually just a nested low-pass filter, essentially. And this is how most cables and wires act, right? We don't, and it's important to realize the R and the C aren't intended whenever we run a wire. Like if we had our way with the universe, whenever we run wires from one machine to another to communicate data, right, we don't want resistance and capacitance. These are actually known as parasitic resistances and capacitances. They sort of just come with the game. But what they say is, like, when you have one machine right over here, and it's maybe over a pair of wires communicating to another machine right here, this one will send out nice clean 1s and 0s, right? And remember the FFT, the Fourier transform, not necessarily the fast Fourier transform, but if you take the Fourier transform of a square wave, right, you're going to get sort of, what am I trying to say, spikes at the frequency of the square wave, and then sort of harmonics of it at some sort of pattern, which we don't need to go into in this class. But basically there's a sum of infinite sines which gives us our square wave shape. But if we superimpose the frequency response curve, which we just generated right here, on top of this, what it's saying is, you know, at the output at the end of the day, the ones in the low frequencies are going to get multiplied by 1-ish, right? So they're going to basically remain the same, but then these higher frequency ones get sort of killed out, right? And then you end up becoming more purely sinusoidal, and all of these higher frequency ones, which are actually responsible for the sharpness on the square wave, end up disappearing, and you end up becoming more sort of like this, or something, I mean something messy. And so usually what happens is whenever we're transmitting data, it's nice and sharp, clean square wave coming out of this thing, but it ends up looking circly, sine wavy-ish on the input. And basically it's a game of how far can we push it and still read these as ones and zeros before we can't anymore, right? And this is actually what limits data rates, or one of the things that limits data rates.